Today, we will see in detail the transition probability for constant perturbation and Fermi Golden rule. I have given this lecture already, but this lecture contains additional information and more clarity. Now we will see the transition probability for constant perturbation. In my previous class on time dependent perturbation, we have seen the expression for uh, probability amplitude for the first order time dependent perturbation. That is ak of 1, which is a function of t, is equal to I H cross inverse integrated over 0 to tau e power I omega kmt brog k h prime get m uh, integrated over time dt. Uh, Here we are perturbing the system at the time t equal to 0, and we are keeping the perturbation up to time tau. So we have put the limit 0 to tau. Here you must keep it in your mind that the wave function, that is a wave vector, initial wave vector get m and final wave vector uh, k are time independent. We have taken time independent in the exponential term. So you can bring this out of integral, and this can be written as in a short form that h prime km, which is equal to this k h prime m. So now our task is to find the integral value of this. Uh, and in order to find the transition probability, this is probability amplitude. If you square it, you will get the probability. So the probability, transition probability uh, for the particle moving from mth state to kth state, that is initial state to final state, which is a function of time, is equal to modulus square of this amplitude, probability amplitude. So if you square this, this is inverse, IH cross inverse. So I have taken that as 1 over IH cross. This is equal to 1 over IH cross modulus square. And this term also I am squaring it, modulus square. And this integrand also I am taking modulus square. Now you solve the term one by one. This 1 over IH cross square, that is modulus square, is equal to 1 over H cross square, and this I am keeping as it is. This, if you integrate this exponential term, you will get e power I omega kmt over omega km between the limit 0 to tau. Of course, you have to square it. So if you apply the limit, upper limit is tau, so this will become e power I omega km tau divided by this omega km. Then lower limit is 0. When t equal to 0, this will become the for lower limit it will become 1. So naturally this will become e power I omega km tau minus 1 divided by omega km whole square. So we have seen that transition probability P from M to K, which is a function of tau, is equal to 1 over h cross squared modulus h prime km whole squared into e power I km tau minus 1 divided by omega km whole squared. Of course, we have modulus. From the trigonometry, that is e power I theta minus 1 whole squared is equal to 4 sine squared theta by 2. So you replace that here. So this omega km, remember that this square is common for numerator and denominator. So I am taking this 4 outside because it's a constant 4 h cross h prime km modulus square divided by h cross square, this omega km square, of course this sine square theta by 2. Here theta is omega km tau. You remember that this is omega km tau. So omega km tau divided by 2 as per this relation. So I am using this fact, trigonometry fact, that e power I theta minus 1 whole square is equal to 4 sine square theta by 2. So I got this expression. Uh, Note that it is yellow color shade. This I can rewrite as in the denominator omega km divided by 2 whole square, because 2 squared is 4. We have seen that transition probability for moving the particle from mth state to kth state is equal to modulus square of the h prime km divided by h cross squared sine squared omega km tau over 2 divided by omega km divided by 2 whole square. Uh, Now we will try to draw the graph for this thing, that is omega km versus sine squared omega km tau over 2 divided by omega km squared, in order to have better understanding. First we will take the origin case when t equal to 0. When t equal to 0, uh, that is when sine theta equal to theta. If theta tends to 0, then sine theta will be equal to theta. That is, this will become this sine squared k omega k sine squared omega km tau over 2 is equal to omega km squared tau squared, because theta is very small. The sine theta, using this fact that is sine theta equal to theta if theta tends to 0. So this is the theta. Here theta is omega km tau over 2. So if you square it, you will get omega km squared tau squared. Here we have 4. That will become divided by 4. 2 squared is 4. Then already there is omega squared km in the denominator. Then this omega km squared in the numerator and omega km in the denominator will get cancelled. So you will get tau squared over 4. So that's what we got the maximum. When omega km equal to 0, the height is tau squared over 4. You got this one. Then when you will get 0, that we will see. That is sine squared omega km tau over 2 must be equal to 0. This will happen only if the argument is a multiple of n pi, that is n is an integer. So then omega km tau divided by 2 is equal to n pi. Then what is omega km? You bring this tau and 2 at the other side, right hand side. This will become 2n pi over tau, 2n pi over tau. So omega km is equal to 2n pi over tau, which is if n is equal to 1, this will be 2 pi over tau. When n is equal to 2, it is 4 pi, 2 into 2, 4 pi over tau. If n is equal to 3, then 2 into 3, 6. You will get 6 pi, 6 pi over tau. So that's what we have. So we got the x-axis, which is a multiple of 2 pi. So 2 pi over tau, 4 pi over tau, 6 pi over tau, 8 pi over tau. This is x-axis is omega km. So now we got the height, maximum height, and x-axis we have found. Then our task is to find the height of the next peak. That we will see now. We got the maximum peak at tau squared over 4 when omega km equal to 0. Then our task is to find next highest peak. Uh, then previous just now we have seen that the next peak which will be 0, omega km will be 0 uh, when this x-axis is 2 pi pi tau, 4 pi pi tau, and 6 pi pi tau, and 8 pi pi tau. Just now we have seen. That is sine n pi is equal to 0, n where n is an integer. It will be maximum. In order to find the next maximum, the sign argument will be maximum if it is multiple of odd integer, that is pi by 2, 3 by 2, and 5 by 2, like that. It will go like that. That is this argument omega km tau divided by 2 must be equal to 2n plus 1. 2n plus 1 is an odd number multiplied by pi by 2. Now this 2 and 2 will get cancelled, and you bring this tau in the right hand side. You will get omega km equal to 2n plus 1 pi divided by tau square. Then see, this argument is 1, then this ratio will become 1 over omega km square. So naturally, the one over omega km squared is just you square this inverse. That is right hand side. You take the inverse and square it, which will be equal to tau square divided by 2n plus 1 whole square pi square. Now, when n is equal to 1, 2 plus 1, you will get the 3. 3 squared is 9. So, when omega km is 3 by tau, then you will get tau squared divided by 9 pi squared. Pi squared value is approximately it is 10. 3.14 into 3.14, it will come 9.8. You can take roughly as 10. So next peak is at tau squared divided by 90. This one. Then next peak is when n is equal to 2, you will get 2 into 2, 4, 4 plus 1, 5. So 5 squared is 25, 25 5 squared. So this will be roughly equal to tau squared over 250. Then next case it is 7, 3. When n equal to 3, 2 into 3, 6 plus 1, 7. 7 squared is 49. So this will be 490, tau squared by 490. You can imagine that first peak is at tau squared by 4, next peak height is tau squared by 90. So it is rapidly reducing one. Then next is still worst, that is tau squared by 250. So this indicates the probability. Then probability is amplitude. Then if you the probability will go rapidly tends to 0 when you are moving away from 0. That is omega km is away from 0. It rapidly, the peak height rapidly decreases. That is a very crucial point. So the when you move the energy, this is the highest energy. Energy is h cross omega km. So when you are moving away from the origin, this energy will partially go to 0. That is very important point. So the height and width of the main peak is centered around omega km is approximately equal to 0. This and decays rapidly. This height decays rapidly. That also we have seen when km moves away from 0. So this is a very crucial point, and height is proportional to tau square. You have seen tau square, and width. This width you can see it is 1 over tau. Width is proportional to 1 over tau. Hence, the area under the curve is width height into width. So lambda square into 1 over lambda, which is proportional to tau squared multiplied by 1 over tau, which is equal to tau. So it is area under the curve is proportional to tau. So since most of the area is under the central peak, the transition probability is proportional to tau. This is proportional to tau. The central peak become narrower and higher as time increases. Remember that time increases means it's coming close to, because this x-axis is 1 hour time. Time increases means it's coming closer to 0. So the central peak become narrower and higher as time increases. This is exactly the property of Dirac delta function. So according to Dirac delta function, it is 1 at 0, and all other places it will be 0. So it approaches the Dirac delta function property. Uh, Hence, this meaning of this is, hence there may not be much difference between initial energy and final energy. Both are almost the same, because energy change takes place only when omega km is very much closer to 0. So initial energy and final energy stays here itself in the peak, which is centered around 0. When you move away, this peak height reduces. The peak height indicate the probability. So probability reduces drastically. So when you move beyond the 0, you will get probability close to 0. So your peak is actually centered around 0. As tau tends to infinite, from the definition of Dirac delta function, you know very well that Dirac delta function is an improper function, but we can make use of proper function as a delta function and under certain condition. Here, delta function can be defined in terms of sine squared function, that is delta x, which is equal to when limit a tends to infinite. This is the condition. When a tends to infinite, sine squared ax divided by pi ax squared. This is the delta function, delta x. Here you can see, compare this equation and this. That is probability, transition probability equation, and this one. You can compare, then you can understand x is equal to omega km divided by 2, this, and tau is equal to a. So then this will become, there is a pi a here. There is no pi a here. Pi a means a, we have taken tau as a. So in the denominator, I am multiplying the denominator by pi tau, and also numerator pi tau, in order to compensate this. So now you can see the term inside the rectangular red color box. Then this is exactly equal to this one. So here is delta x. This is a red color rectangular box is delta x box. But you know x is omega km divided by 2. Of course, we have this pi and tau. Now the transition probability from m to k is equal to, which is a time dependent, is equal to modulus square of the h prime km divided by h cross squared delta omega km divided by 2 into pi tau. Now we will see the transition rate for constant perturbation, because seeing this transition probability moving from m to k is equal to, just now we have seen this h modulus square of h prime km divided by h cross squared delta omega km divided by 2 pi tau. But you know the omega km is equal to ek minus em divided by h cross. So I am replacing omega km by ek minus em over h cross. Of course, this 2 is here. So this will become like this, and pi tau as it is. Uh, Using the property of Dirac delta function, that is delta ax is equal to 1 over modulus a into delta x. Here a is 1 over 2 h cross. So that means 1 over 2 h cross will become 2 h cross just. So it will come into the numerator using this property. So 2 h cross pi tau h prime km modulus h prime km square divided by h cross squared into delta ek minus em. I have used Dirac delta function property. Here h cross will get cancelled with this h cross square. So you will get only h cross in the numerator, sorry, denominator, and tau in the numerator. Now you can find the transition rate, which is defined as transition probability per unit time. That means you divide this p by tau, then you will get the transition rate. So this tau will become to the left hand side, which is equal to, by definition, gamma m2k is equal to p m2k, which is a function of tau divided by tau, will be equal to 2 pi over h cross. This h cross will come. Of course, by definition, this h cross km whole square, which is nothing but k h prime m whole square. Of course, this delta ek minus em. Of course, we have taken this to the left hand side. This is the transition probability. Sorry, transition rate. So we have seen the transition rate, which is equal to p by tau, is equal to 2 pi by h cross this k h prime m modulus square delta ek minus em. See, we have defined the delta function based on the fact that tau tends to infinite. Tau tends to infinite. Uh, Under this condition, this delta function is valid. That means ek must be equal to em. Delta ek minus em guarantees the conservation of energy in the limit tau is tends to infinite. So this transition rate is non-vanishing, only the state of equal energy. That is a very crucial point. You can see tau is infinite means it is not moving away. The x-axis is 1 over tau. So it is coming closer to zero origin. At the origin, this you can find the particle. When you are moving away from the origin, then probability of finding the particle is very much less than 1. Your particle is centered around 0. Omega km is equal to 0. That is ek minus em is equal to 0. So it is clear that transition rate is non-vanishing only between the state of equal energy. Even if it is a variation, that variation is very small and that is close to 0. Hence, the constant perturbation, that is time independent perturbation, neither remove the energy from the system nor supply the energy to it. It is the energy conserving transition. This is energy conserving transition. Uh, Now we will see the Fermi Golden rule. The total transition rate associated with a transition from an initial state to UM, we have taken in the Dirac notation get M into continuum of final state UK, that is bra K. Uh, Let us say rho, which is a function of EK, is the density of final state. Then number of state per unit energy interval, that is number of final state within the energy interval Ek and Ek plus TEK. See, I have established that this initial energy and final energy is there is a very small difference. So we are going to find the number of state between Ek and Ek plus TEK. Then the total transition rate, which is equal to WKM, is equal to, you have to integrate P divided by tau rho Ek. This is initial energy state. So our aim is to find the density of state between initial energy state and final energy. Ek varies from only Ek between the plus between Ek plus and Ek plus Tk. So I am integrating over Etk. By definition, we have seen uh, uh, P M2K tau divided by tau. That is transition rate. Just now we have seen is equal to 2 pi, which I have shown in the yellow color highlight. 2 pi over h cross h prime km modulus squared delta ek minus em rho ek dek. Since 2 pi by h cross and this term modulus square of h prime km is a constant, we are taking out. So in the integral you have delta ek minus em rho ek dek. So the total transition rate WKM is equal to 2 pi over h cross modulus square of h prime km integral delta ek minus em rho e of k dek. This delta function, this integral will gives you, this integral exists only when Ek is equal to Em. So this can be written as rho Em, where Em is the initial energy state. This relation is called Fermi Golden rule. It says that in the case of constant perturbation at sufficiently long time, that is tau tends to infinite, the total transition rate become constant. That is time independent. There is no time dependent factor. This modular square of first term is a constant. So next term modular square of the h prime km also constant. The initial density of state also constant. So it is independent of time. That is called Fermi Golden rule. Thank you very much for watching my video and supporting me continuously. Thank you very much.